Okay, so I got a glowing report from Mr. Vukowicz about you guys yesterday, saying you're focused and you got about this far. Okay, did you finish the practice questions or just get started on it? Finish them? Okay, so you've seen the solutions. All right, so let's just quickly review yesterday. Okay, Newton's second law deals with all the situations where there is now a net force, or there's a force that's not balanced, and those forces cause changes in velocity. Okay, so it breaks down to, F net equals mass times acceleration, which seems like, oh man, this is going to be so easy. Okay, except it's very rarely that simple. Yes, that's a three-variable formula. It's like V equals d over t. The problem is getting to F net, because this formula isn't finished. F net is m times a, but it is also the vector sum of all forces. That's where some of the complexity comes in. Okay? We still have to do vector addition. We have to be able to identify all the forces that are acting on an object, determine the direction in which they are acting, and then move to, oh, I can calculate the acceleration now because I know the mass of the object. Okay? Suffice it to say, the number of situations that Newton's second law applies to is staggering. We can't cover them all, okay, in the time that we have. But we will cover as many as we can in terms of the most important ones, okay, the ones that can help you to extrapolate what you know to Newton's second law to the most or the highest number of situations. Okay, so these ones here, these are pretty basic. Right? You have the net force, or you're calculating the net force, and you have the acceleration. Okay, so simple, pretty simplistic ones there. Let's have a look at one that's a little, it's not a lot harder, but you have to think a little bit more on this one. Okay, so I'm going to give you a minute here, copy this one down, and then we'll walk through it together. Okay, so give you a minute here, just get that copy down. Okay, so the first step in any Newton's second law problem is to draw what kind of diagram? The simple one. Okay, what was the name of the simple one? Free body diagram. Okay, so in a free body diagram, okay, I'm going to draw just a box. I don't have to draw a pretty picture. Okay, so what mass am I putting in there?
The mass of the canoe and the two people.
Right, the mass of the canoe and the two people. That's the trick with this. People forget about the two people in it. Right? They just, well, they're accelerating the canoe, and they just look at the mass of the canoe. Well, they're in it too, okay? So you have to put them in there as well, right? So we got 65, 135, and another 20. So 155 kilograms, if my mental math is right there. Okay, so I got 155 kilograms worth of mass being accelerated. Athlete A can row 400 newtons forward. Okay, so there's one forward force acting on the canoe. Okay, the second athlete can exert 420 newtons, so just ever so slightly longer, 420 newtons forward. And in the water, there is a resisting force of 380 newtons. So resisting means going the other way. All right, now I've got my free body diagram. Because all these forces are collinear, they're forward and backward, I don't really need to draw a vector diagram for this. I can just go forward is positive, backward is negative, add them all together. Everyone okay with that? Okay. So I'll have my 820 newtons forward minus 380 newtons backwards. Okay, so 820 minus 380. All right, so we got 440 newtons. Okay, in a forward direction. All right, so now I have my net force. I've used my free body diagram, and I have found the vector sum of all the forces that were acting on the mass. And you're going to do this in basically every question. It's always going to be the same steps, not always in the same order. Okay, but you are always going to draw a free body diagram. Okay, find the vector sum of all forces, and do F equals m times a. But sometimes you do F equals m times a first, and then you'll have to find one of the missing forces using vector sum of all forces. Okay, it changes the order, but it's always the same steps. Now that I've got the net force, now I can go to this formula. F net equals m times a, divide both sides by the mass, and I'm finding the acceleration, 440 divided by 155. So this is newtons divided by kilograms. Now remember, a newton is a kilogram meter per second squared. So if I divide kilogram meters per second squared by kilograms, I should be left with the units for acceleration. Agreed? Okay, so to two significant digits, we have 2.8 meters per second squared forward. 2.8 meters per second squared forward. Okay, everybody all right with that one? Nothing too crazy there? Okay, but it's the first one where we actually had to combine a bunch of forces. All right. No questions, we'll move on. Okay, try this one. This one's not any more mathematically difficult than the last one, but you have to read it carefully. It might give you some information that is extraneous, okay, or unnecessary. Give you a few minutes on that. Okay, so in the men's four-man bobsled, the maximum mass of a bobsled with 2 riders, a pilot, and a brakeman is 630 kilograms. Okay, so they have an upper limit on how heavy everything can be, because if you add more weight, you gain more energy, right? Because energy is based on mass. So if you have more mass in there, then you can have more energy, which can mean that you might have a higher speed, okay, under certain conditions. So that's our maximum mass. Do I need that piece of information at all? It's completely extraneous. During the part of the question that we're dealing with, there are still 2 people outside of the sled. Only the pilot and the brakeman are in the sled. The other 2 guys at the back are pushing. Okay? Now, I don't know if you've ever watched this sport, but the people who do bobsled are usually quite powerfully built people. Okay? They're usually people who were sprinters in track and field, but didn't have a high enough top speed to win. Okay? But they were very, very powerful accelerators, so they could exert a lot of force, which makes them great for the bobsled, because top speed doesn't matter. It's how much can you push. Okay? So being able to push is the most important part. So during a practice run, riders A and B exert forces of 1,200 and 1,220 newtons. So I'm going to draw my box here. I don't have a mass in it yet, but I am going to put those 2 forces on. 1,200 newtons and 1,220 newtons. Okay? Each to accelerate the bobsled with a mass of 225 kilograms, a pilot of 98 kilograms, and a brakeman 97 kilograms. Okay, so we would have 420 kilograms is the mass there. That's being accelerated because the other 2 guys are still outside and their mass isn't counting. Okay, and they jump in for a challenging ride down the 1,300 meter course. Do I need that number? Okay, so I should probably start crossing off numbers that I don't need because I don't want them to throw off my significant digits at the end. Okay, if I don't use them, they don't affect my significant digits. All right, during the pushing, the magnitude of the force of friction on the sled is 430 newtons. Okay, so much smaller than the other 2 forces I drew on there. Calculate the average acceleration of the bobsled pilot and brakeman. Okay, so first thing I've got to do is calculate my net force using the vector sum of all forces. All right, so we've got 1,200 plus 1,220. Okay, so that's 2,420, and then, whoop, not equals, minus 430. Okay, so that should give us 1,990. Yeah. I'm on a roll here for mental math today. Newtons, and that would be forward. Okay, so we've got that going forward, and we know the mass. Now I can use F net equals m times a. Have we done all the steps that I said we would do in every question? And I'm going to beat you over the head with that continuously. Here's this step again, here's this step again, to just reinforce it. We're always doing those. Okay, so the acceleration will be our net force, 1,990 newtons forward, okay, divided by 420 kilograms. Okay, and that should give us our 4.7 meters per second squared. Actually, yeah, because we used those numbers there, which only had 2. Okay, 4. Okay, questions on that?
What's the top speed of the bobsled?
No idea. They can go fast. Yeah, they get roaring down those tracks if you've ever seen them. All right, now, this is an elevator question. They're kind of the example of Newton's second law that we refer back to most often because it brings the force of gravity in. Okay, we deal with the force of gravity as part of net force a lot. All right, so what I want you to do is in your notes, okay, write in like big letters, elevator example. Because we are going to do all kinds of questions, but elevator, okay, questions always come up. Anything that's moving vertically up or down, even if it isn't an elevator, is technically an elevator question. Okay, because it involves gravity in its calculation. So I'll give you a minute here to get this one written down. Okay, and get the free body diagram there kind of drawn, and then we'll go through it together here. Okay, so the thing with elevator questions is that we are now dealing with individual forces that we need to calculate on their own. Okay, so this brings in the idea that if net force is mass times acceleration, any force is mass times the acceleration that that force would produce in isolation. Okay, that is, if that was the only force acting, here's the acceleration that it would produce. Okay, that is why on your formula sheet you have this formula. The force of gravity is mass times the acceleration due to gravity. Okay, gravity is one of those forces that we can calculate in isolation. And we know that if gravity is acting in isolation, an object will fall at 9.81 meters per second squared. Okay, that sort of makes sense? Okay. So yes, this formula is true when we're talking about net stuff, but it's also true when we're talking about individual forces within the system. Okay, now that's probably the first time you've heard me use that word, okay, in Newton's second law as well. Okay, system means the mass or masses and all the forces that are acting on them. Okay. Okay, so free body diagram of the elevator, okay? We can simplify it, yeah, it's got a picture of the guy inside, okay? But really, this is what we know. There's 600 kilograms worth of mass being lifted by the elevator motor. Okay. What is the elevator motor lifting? Right, but it's working against the elevator's weight, exactly. This is where using the term weight is appropriate. Okay? The cable that's lifting the elevator is working against the force of gravity pulling on the mass of the elevator. That is the weight of the elevator. Okay? If this was on Mars, the elevator wouldn't have to work as hard. Because even though the elevator, the box, would have the same mass, gravity on Mars is 1/3 of what it is here. Okay? It would be working against 1/3 of the weight that it would here. Okay, so this is where working against the weight is actually being used correctly. So if I know the mass of the elevator, can I find the weight of the elevator? Again, I just have to multiply the weight, or sorry, the mass. I almost did it myself there. Okay, the mass of the elevator by 9.81. Okay, so that should be 5,886 newtons if my mental math is right. Okay. Okay, so I know that the force downwards is the force of gravity, and it is 5,886 newtons in a downward direction. The question tells me that the cable is exerting a force of 6.5 times 10 to the 3 newtons up. Anytime you're exerting a force through a rope or a cable or anything else that you can tie to something and pull on, we call that force tension. Okay? That is the tension that would be in the cable or the rope. Okay? So that force upwards, okay, force tension, or you could even say the force applied if you wanted, okay, is 6,500 newtons. No other forces are mentioned, so we're going to assume that it's frictionless because they don't say anything about friction here. Can I find the net force acting on the elevator? Okay, so now I need to find the vector sum of all forces. So F net, okay, will be 6,500 newtons up plus negative 5,886 newtons down. Okay, or just subtract, no matter which way you do it. Okay, so that should give us 614 newtons up. Okay, I have a net force. What's the elevator doing?
Lifting.
Yeah, but how is it lifting? It's accelerating. That's the key part of this. There's a net force here. So there is going to be an acceleration upwards. Now, you've all ridden in an elevator in your life. Does an elevator accelerate all the way up and all the way down? Like, when do you feel the elevator accelerate? Right at the beginning. Elevators, for the most part, travel at a constant velocity during most of the trip. If an elevator accelerated up the entire time, it would be very dangerous. Okay, because it would be going really fast by the time it got to the floor it was getting to. Okay, so they accelerate and get to their lifting speed, and then they stay there. Even the high-speed ones they use in big skyscrapers in like New York or places like that, okay, those accelerate slowly for a longer period, and then they travel at a constant velocity until they get to the floor they're looking for. Okay, but you felt this in an elevator. Okay, when the elevator first starts to lift, you feel the floor push against your feet. Okay, it's pushing on your feet harder than it did when it was just sitting still. Okay, that's what's accelerating you up. Okay, when the elevator starts to descend, you actually feel,
Gravity.
well, you still feel the gravity, but do you feel heavier or lighter when the elevator accelerates down? Anybody ever tried to jump when the elevator is just about to accelerate downwards?
It shakes a lot.
It shakes. You shouldn't do it. It's actually not safe to do it. But you feel a little bit lighter when the elevator first starts to accelerate downwards because the floor doesn't push on your feet as hard. There isn't any less of you. Okay? Your weight is still the same, but you don't feel the same force against your feet. So you actually feel lighter, okay, when the acceleration is downward. All right, so we can now calculate we have our net force, so we can now calculate the acceleration. F net divided by mass. So 614 divided by 600. So this is newtons, this is kilograms, okay, and we'll get our meters per second squared. So 614 divided by 600. Okay, so the acceleration upwards is 1.02. I think we have 3 sig digs there, so 1.02 meters per second squared up. Okay. Does an elevator still pull up when it's lowering you? It does. Okay? The cable is still working. It's just the motor's not exerting enough force to lift you. It's only exerting enough force to not let you die. Okay, by not letting you accelerate down with a net force of just your weight. Okay, so there's still a pull upwards when you're being lowered. Think about this, like if you were, if you had a big heavy box attached to a rope and you were lowering it off the roof of a building, you don't just go let go of the rope, and whatever's in that box is toast, because then the net force is just gravity. You still pull upwards and you lower it down. Now, if that elevator is going to travel at a constant velocity, okay, this 600 kilogram elevator, how much force does the cable need to exert?
Gravity.
Right, the same as gravity. Okay, remember, this is Newton's first law now, and we always come back to this. If the object travels at a constant velocity, what's A? 0. If A is 0, so is this. Would you agree? And if this is the vector sum of all forces, then if it's going to travel at a constant velocity, you've got to have 5,886 up minus 5,886 the other way. Now it'll travel at a constant velocity. There will be no acceleration. That kind of thing comes up all the time. Here I gave you the acceleration, it was 0. Find one of the two forces that's acting on it. It kind of makes it go backwards. Okay, remember I said it's always the same steps, but not always in the same order. Okay, that one's making you work backwards a little bit. Okay, calculate for me what the acceleration of this system would be if the force upwards is now 5,000 newtons. Okay, so if we change the force that the elevator exerts now to 5,000 newtons, what's our net force? 886 newtons down. Okay, so now we still go back to this, but instead of having 614 newtons up, now we're going to have 886 newtons down. Okay, so that's our net force. Now we divide that by our mass. Okay, so 886 divided by 600. Okay, so now the elevator is going to accelerate at 1.5 meters per second squared down. Okay, it still needs a vector on it. Okay, you would feel lighter there. Okay, you would probably only feel about 85% as heavy as normal. Okay, in other words, the floor would push on your feet with about 85% of its normal force. Okay. Now, there's a term I've used a couple of times before, but we're going to hear it a lot more. Normal force. Okay. Normal force is the force that right now the floor is exerting on my feet. Right now, that normal force is equal to my what? To my weight. Okay, gravity is pulling my mass down, okay, with a certain number of newtons that we won't bring up. Okay, and then the floor has to push up with exactly the same number of unmentionable newtons, okay, so that the net force ends up being 0. Everybody okay with that? Okay. So this is another elevator thing that comes up all the time. It's a strange situation because I've never seen anyone do it except myself and Mr. Dickey. A person is standing on a bathroom scale in an elevator. Okay? The bathroom scale always shows your what? Well, under normal situations, it shows your mass by reading your what? Your weight. Okay? So let's just imagine this bathroom scale actually shows us a number in newtons. So it tells us your weight. It actually doesn't tell you your weight. It tells you your apparent weight. It tells you how heavy you feel, because you can change that number. Anyone ever jump up and down on the scale? Does the number go like this? Because if I bend my legs and push, do I push on the scale harder? I'm not any heavier though, am I? Okay, but the scale tells me I am. Well, the same thing would happen if I stood on a scale in an elevator. If I'm standing on a scale, Mr. Dickey and I did this in the elevator here in school one day just for fun, okay, because we're nerds, that's who we are. Okay? So we stood on the scale, and when the elevator went up, what happened to the reading? It read heavier, because the floor has to push on my feet with more force. In fact, if I was doing this, okay, the reading I'd see on the scale is the upward force for the elevator. It would tell me how hard the floor of the elevator has to push on my feet in order to accelerate me upwards. It only shows that for an instant, okay? Because it only accelerates for a very short time, and then it travels at a constant velocity after that. But here's the weird thing. When we got to the top floor, and the elevator stopped, what did our weight read for an instant?
0?
Well, lighter, not 0. But when the elevator came to a stop, did my inertia keep going up? So I didn't push on the scale as hard, right? So for an instant, I was lighter, and I liked the number, okay? And then reality came crashing down as I came crashing back down on the scale with my full weight, okay? When we descended the elevator for the first instant, it went back to that nice light number that I liked, okay? It actually read that I was about 15 pounds lighter, okay? Which, that's great, I'd love to be 15 pounds lighter, okay? But it read that my weight had gone down. Okay? If my weight didn't change, the force of gravity is still pulling on me with the same amount, but the floor doesn't push on me with that amount. And that's why I accelerate down. Okay? The force down is greater than the force up. So when you encounter an elevator situation that sounds crazy, because it is, a person standing on a bathroom scale in an elevator, they're telling you whatever the scale reads is the upward force. Okay, the force pushing on your feet. And then your actual weight would be the downward force. So you'd have the force of gravity here, and then this would be our normal force, the force the scale is reading. Okay, everyone follow on that? It's weird, but it's a situation that comes up all the time. Person standing on a scale in an elevator. Okay, no one but physics teachers have ever really done that. Okay, but it's a situation that comes up. Okay, let's have you guys try number 1 there. Okay, so same elevator. I'll just put the numbers back up here. Okay, so it's the same elevator. Still has a mass of 600 kilograms. Okay, find the acceleration of the person when the force is 5,000. The elevator cable is using 5,200 newtons worth of force. No, stop. I want to do it different. Let's try this. We haven't done one in this order. Now I'm telling you the acceleration of the elevator. Okay? I want to know what's the tension in the cable, okay, or the force the cable is exerting upwards if the elevator is accelerating downwards at 1.1 meters per second squared. Okay? See if you can figure that one out. It is a little bit backwards, but think about what you have. Okay? You have the force of gravity, or at least the ability to calculate it. You have the acceleration and the mass. There's something you can calculate with those two numbers that might help you get to the force you're looking for.